Let's continue with this question about trying to identify the span of a set of vectors. So we'll just look at a couple more examples. So for example, if we are in just R2, if you take any generic vector, so here's a generic vector in R2, right? So that's some element of R2, and I'm making no assumption about what A and B are. That's what I mean by generic. I can always write this as A times 1, 0 plus, B times 0, 1, just using vector arithmetic. So this shows you that any element of R2 is in the span of 1, 0, 0, 1. And so in other words, the span of 1, 0, 0, 1 is all of R2. And so it turns out that this works, well, if you notice here, 1, 0 and 0, 1 are the columns of the 2x2 identity matrix. And so in general, the columns of the n by n identity matrix, which I'll denote by I sub n, span Rn. And we call this the standard basis. The standard basis for Rn. We'll talk later on about this word basis, which is a specific technical term, but for right now you can just think of it as the standard spanning set, although basis requires more than that. So let's see. So let's look at another example. What is the span of V1 given by 4, 0, 2 and V2 given by 1 minus 1, 1? Well, so what are we looking at? We've got okay, so let's take the x-axis going this way, or the x-axis. Okay, and the y-axis going this way, and the z-axis going vertical, like we do. And so then 1, 2, 3, 4 out on the x, 0 on the y, 2 up. So we've got some vector that looks like this. Actually, let me make them a different color. So we've got some vector that looks like that. And then for V2, we go 1 and then negative 1 and then up 1. So boom, 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 over here somewhere. So we've got that. Okay. So then the span of these two vectors is going to be everything that I can make as a sum of these vectors. So this is now looking at this coordinate grid here. So we have this plane, and so anything that you can get to, these green vectors, this green plane here, this is the span of V1 and V2. So it looks like some plane, some two-dimensional space in R3. So you can also ask, what is the span of, and let's take the Same stuff as before. But then we'll also throw in, let's call it u. And u will be -1, -3, 1. All right, so what is the span of these guys? So let's draw in this one. So -1, 3, 1, that actually turns out to be the reason why I chose this vector is because this was minus v1 plus 3v2. So out here somewhere. So there's u. But u is in the green plane, right? Because I was able to make it out of some number of these vectors and some number of these vectors. Oh, here, let me get the highlighter. Some number of these vectors and some number of these vectors being added together. So -1 of these, that would take me out to here. And then adding 3 of these would take me bing, bing, bing. Okay, maybe I drew it sort of poorly, but you get the idea. So that one's still in the plane. Now, what if we asked the same question, except instead of this third one here, we did v3 given by, and we take the one that we had before, 1 minus 1, 2. Okay. Well, then what we saw is that the determinant of the matrix, where if I put in these vectors as columns, so this is my notation for putting in v1, v2, and v3 as the columns of some matrix. So if we did that, we saw that the determinant was non-zero. And if the determinant is non-zero, that is equivalent by the characterization of invertibility theorem to saying that the system with v1, v2, v3 as the coefficient matrix times c equals b can be solved for c. Okay, and if that's true, that is just another way of restating by the definition of matrix multiplication that c1 v1 plus c2 v2 plus c3 v3 equals b can be solved. So in other words, we can find coefficients c1, c2, and c3. That'll make that work. So let me reinterpret what this is saying. This is saying that every vector b in R3 is in the span of v1, v2, and v3, because I can always solve that equation. And if everything is in the span, then that means that the span is R3.